I'm going to talk about invertibility of random matrices in broad terms. And this problem has seen a tremendous progress in the last 2 years. So I'm going to talk about the new results, but before it, I will discuss the approach to the problem through the geometric method. So what is it about? Let's start with a simple problem. Assume that we have a matrix A, n by n, and the entries A, I, J are all independent, identically distributed, and symmetric plus minus ones. And we'll ask ourselves a question, what is the probability that such a matrix is singular? The problem looks naively very easy, but it's actually extremely difficult, and the full answer, even the precise asymptotic answer, is still unknown. What we can say that this probability is greater or equal than 2 to the negative n, because this is the probability that we have two identical rows, but actually we can do a little better than that. We can have also two identical columns, and we can choose the pair of these rows and columns. So this is about 1 squared. And it's conjectured that this is more or less a precise estimate, namely the main reason for the invertibility, for the singularity of such a random matrix, is that it has two identical rows or columns. This is open, but about less than 2 years ago, there was a big breakthrough by Tikhomirov, and I'm going to talk about it in the second lecture. But how would we approach such a problem? First of all, this direct approach is not going to lead us anywhere if we want to just estimate the probability that the determinant is 0. The entries in the determinant are so convoluted that we lose all track of independence, and independence is our major tool here. There is another problem which is close to it and which has a lot of practical applications. This is a quantitative singularity. Here, we estimate the probability that the matrix is singular. We can ask ourselves, given a matrix, how far is it from the set of singular matrices? And we can estimate the distance, say, in the operator norm, in the spectral norm of the matrix. And this leads us to the smallest singular value. So if we have a matrix A, we can consider the matrix A, real or complex A conjugate, and we can consider the eigenvalues of this matrix. If we take these are non-negative numbers, so if we take the square roots, we get what is known as the singular values of A, and we traditionally arrange them in the decreasing order. So the most important singular values here are the first and the last one. The first one is just the operator norm of the matrix. The last one, the least singular value, is actually the distance of our given matrix to the set of the singular matrices in the operator norm. Besides being the distance, so when we consider the distance, we can ask ourselves, what is the probability that this distance is less than epsilon for a given epsilon? And this has a lot of practical applications. One of those is that if we consider the condition number of A, which is the ratio of the maximal and the minimal singular value, this governs the convergence of virtually all algorithms in numerical linear algebra. The second reason, if we want to prove limit theorems for random matrices, what we frequently need is exactly the bound for such probability. For example, if we take a sequence of matrices AN, where these are n by n matrices, and the entries are copies of the independent copies of the same random variable, we normalize them properly. The proper normalization here is 1 over square root of n. Then this is a sequence of complex random matrices, and the complex or real random matrices, their eigenvalues are complex, and it turns out that with probability 1, the empirical distribution of these eigenvalues, these are discrete random measures, they converge to a deterministic measure, namely the uniform measure on the unit circle. This is called the circular law. And to prove the circular law, you need a strong bound on the least singular value. Okay. By the way, let me make 2 remarks. First, if you want to ask a question, please don't wait till the end of the lecture. Stop me immediately. And second, I am not going to discuss the history of the matter. So I'm going to omit almost completely the story of who did what. I apologize for it, but we don't have too much time. So how to approach this? Let's look at these singular values, all these singular values, and we can look at them geometrically. If I take the Euclidean unit ball and act on it with the matrix A, I'll get some ellipsoid. The linear image of the ball is an ellipsoid. And the longest semi-axis is S1 of A. The shortest one is Sn of A. So this condition number actually tells us how much the matrix distorts the Euclidean metric. All right, so how would we approach these invertibility questions? We have two questions. One is the qualitative invertibility, the probability of singularity. The second is the quantitative invertibility, is the estimate of the distance to singular matrices. And actually, the singularity means that the smallest singular value is exactly 0. Well, let's take this picture and try to use it. This is the Euclidean metric. So S1 of A is the maximum over the unit sphere of the norm of the Euclidean norm of AX, and Sn is the minimum of the same thing. And so we have to bound the maximum and the minimum, hopefully with high probability. But let's take a more modest task. Let's fix a vector x and see how this norm behaves. In the sphere. And I will assume that the matrix A has IID entries with expectation 0 and variance 1, for example, and then it's an elementary calculation that if we take the norm of AX and square it, this is a quadratic form of the entries of X, so it's easy to take the expectations, sorry, here it's 0. The mixed terms disappear because the entries are centered. The squares contribute 1, so we have the sum of squares of the coordinates times and this is going to be m. Well, and if the matrix has the matrix entries have light tails, for example, if they are bounded, then the random variable norm AX is concentrated about n, and we can conclude that the probability that, say, 1/2 square root of n is less or equal than the norm of AX less or equal than twice square root of n is almost 1. Actually, it is at least 1 minus e to the negative cn. In this lecture series, I will denote by c small, c capital, etc., the absolute constants. Okay, so this is what we know for one vector. And of course, if we know it for one vector, we can use the union bound and have it for many vectors. We want to have it for the whole sphere, but the sphere is uncountable, so we cannot just use the union bound, but we almost can do it. We'll discretize the sphere and take an epsilon net in the sphere. An epsilon net is the set of vectors which approximate any vector in the sphere up to epsilon. And then if we are able to prove the uniform bound on the epsilon net, we will this bound will propagate to the whole sphere. Let's see. We want to use the union bound on the net, so we need the cardinality of the net. There is a standard estimate in geometry, the volumetric estimate. It is less or equal than, say, 3 over epsilon to the power, which is the dimension of the space. Okay. So the probability that the norm of AX is greater than, say, 2 square root of n for some point in the net is less or equal than the cardinality of the net times the failure probability, which I know to be e to the negative Cn. And if this is much smaller than 1, we are happy. We will then extend it to the whole sphere. If the constant is just 2, we are not sure about it. Here I have 3 over epsilon to the power n, but I have some flexibility. I can replace this 2 by a larger constant, some constant k, and then this c is going to be replaced by c of k. If I make k larger, this c of k will be larger, and it will tend to infinity just from elementary concentration. So we will be able to overcome this union bound barrier. We'll prove it, and we will conclude that with probability exponentially close to 1, the norm of A is less or equal than k square root of n. So the first singular value is very clear. Let's try to do the same with the smallest singular value. And again, we do the same, the probability that there exists an x in the epsilon net such that the norm AX is less than 1/2 square root of n, is less or equal than the cardinality of that 3 over epsilon to the power n times e to the negative Cn. And again, we want to figure out what is this product. Both terms are exponential in n. What wins? First of all, let's understand what epsilon is. If I take any y in the sphere, I can find x, which is an approximation, in an epsilon such that the norm of x minus y is less than epsilon. And then I can use triangle inequality. So the norm of ay, I want to propagate my estimate. The whole sphere is greater or equal to the norm of ax minus the norm of a times x minus y, which I can estimate above by norm of a times x minus y. This is smaller than epsilon. This is, as we already figured out, at most k square root of n. So, and this is going to be greater than 1/2. So to make a meaningful estimate, we need epsilon to be less than 1/2 square root of n. Epsilon to be less than 1/2k. And then we plug it into this bound. And it turns out that the product is going of these two terms is going to be exponentially large. And C is going to be greater than 1. So this estimate is vacuous. We failed completely with this epsilon argument. But nevertheless, let's look how we failed. It's not by much, it's by exponential term. So the conclusion is that if we are able either to improve this term, which is the probability that the norm of a fixed vector is less than 1/2 square root of n, or to improve this term, which is the size of the net, we can fix it. Let's see if this is at all possible. Here I have a freedom of replacing this 1/2 by any constant. But if I do it, the best I can hope for is say that the entries of the matrix A are IID normal, and then the image of any vector is a standard Gaussian vector, and I can write that the probability that AX is less than T square root of n is going to be less or equal than some constant times T to the power n. Or let's say if I have here epsilon to the power n, C epsilon to the power n. And then I have the same product. If I take a union bound, I have C epsilon to the power n times 3/epsilon to the power n. And this still is going to be much greater than 1. I do, but this is encoded in epsilon. I can take epsilon depending on n. But even if I try, in the best world, I'll get this. If the small ball probability holds for any epsilon, I still am not able to do anything with this product. Maybe we can improve the net cardinality. It turns out that in general, it's impossible. This is a precise estimate. So we failed completely. But nevertheless, keep the mental note that we didn't fail by much. We failed by a constant to the power n. But still we failed, so we have to produce something completely different. And let's consider an alternative idea. The alternative idea is, let's take a typical point on the sphere. Well, how does the typical point look like? All the sum of the squares of the coordinates is 1. So each coordinate is about 1 over square root of n. And typically, the absolute value of all xj is about 1 over square root of n. What can we do with that? Let's consider the matrix AX, the image of this point, and this is the sum j from 1 to n, AJXJ, where AJ is the jth column of A. Well, if I know one of those and I can eliminate the impact of others, then there is no cancellation and I will have a bound, a lower bound. So let's try to eliminate the other columns. To do it, I'll take a unit vector such that it is orthogonal to all A columns AK, where K is different from J. And then the norm of AX is greater or equal than the absolute value of the inner product of AX and U. Let's call it UJ. Okay, and here I write AX as the sum. I use the fact that U is orthogonal to all AKs, and I'm left with just one term, AJXJ, inner product with UJ. And I know that the absolute value of xj is about 1 over square root of n, so it's greater or equal than 1 over square root of n, AJXJ. What did we gain by this calculation? If you look at the right-hand side, UJ, X is completely gone from the picture. So we don't have to take the union bound. This is all we need is to bound this inner product. So if I know that the probability that absolute value of A J U J less than T less or equal than some U of T, then for all vectors with the jth coordinate about 1 over square root of n, I get a union bound. But in general, I don't know that the jth coordinate, the prescribed jth coordinate, is large. It may be just 0. So what to do then? Let's introduce another source of randomness. Let's pick the coordinate randomly. And then I will have the product of AJ and UJ with J random. But this doesn't make my problem any harder because the entries of the matrix are ID, independent identically distributed. So this probability actually doesn't depend on J. And as long as I know that a random coordinate J satisfies this bound, is of order 1 over square root of n with constant probability, I am in a good shape. I can carry this argument through. But this is also not the end of the story. We can imagine vectors for which all the coordinates are small with probability close to 1. For example, if I take a basic vector 1, 0, 0, 0, the probability that a random coordinate is large is 1 over n. So what to do in this case? Let's separate them. When does the vector have only a few large coordinates? So when a random coordinate is small, it means that only a few coordinates are large. But it means that it is close to a coordinate subspace of a small dimension. So it is almost sparse. Such vectors are called compressible. And so they are well approximated by the sparse vectors. And what is the advantage of dealing with the sparse vectors? Let's recall how we constructed this net. We have a volumetric estimate, and epsilon is less or equal than 3 over epsilon to the power of the dimension of the space. Now, if the vector is sparse, then we are interested only in the support of the vector. The support is much less than n, so the dimension of the relevant space is much smaller than n. And this much smaller is exactly the improvement we needed to carry the epsilon net argument through. So we beat this additional absolute constant to the power n. And if the vector is sparse, we can conclude that the norm of AX is greater or equal than c square root of n with probability close to 1 for all x sparse. So we are happy about that, but if we don't know this uniform bound for the sparse vectors, here the constants may be different, we can extend it for the vectors close to sparse. So for all compressible vectors, and then the vectors for which we have few coordinates which are large do not constitute a problem. So the conclusion of all this story is that if we treat the compressible vectors separately, we are going to reduce our minimum over the sphere So the probability that Sn A is less than epsilon. Now let me write, and then I'll explain. Epsilon over square root of n is less or equal than the probability that the inner product AJ UJ is less than epsilon plus e to the negative Cn. Okay, why this is epsilon over square root of n? If we go back to our bound, our calculation here, we see that we lose this square root of n because the typical coordinate is 1 over square root of n. But we were able to reduce the minimum over the sphere to just the bound, the lower bound on the probability that, sorry, the upper bound on the probability that this inner product is small. And this additional term is responsible for compressible vectors. Very well. So our task is only bounding this small ball probability, and this pertains both to the smallest singular value estimate, and if we take epsilon equals 0 to the singularity probability. We said for a random j, but for a fixed j, it doesn't depend on j. I can write 1 here. So what do we have now? This is a random vector with IID coordinates. This is also a random vector with who knows what coordinates. But let's look at U1. We said that it's orthogonal to A2, A3, etc. A. And so it depends only on those vectors. In particular, it's independent of A1, which means that if I condition on the other columns of the matrix, I can regard U1 as a fixed vector, and we have the product, the inner product of a random vector and a fixed vector. Is the sum A1 J U1 jth coordinate, j from 1 to n. And this is a linear combination of IID random variables. We reduce the problem from a difficult one, namely the singular value of a matrix, which is a nonlinear function of the entries of the matrix, to a very simple one, the linear combination of IID random variables. What can we say about it? Let's consider an ideal situation when the entries of the matrix are n, 0, 1, standard normal random variables. Then the linear combination of independent normal random variables is normal The expectation is 0 because the expectation of all of those are zeros. The variance is the sum of the squares of the coordinates of u. U is a unit vector. So this sum a 1j u 1j is also a normal random variable. Perfect. So in this case, we can say that the probability that u1 is less than epsilon is less or equal than the epsilon for all epsilon greater than 0. And it means that the probability that the smallest singular value of the Gaussian matrix is less than epsilon over square root of n is bounded by a constant times epsilon, maybe plus this exponential. This is underwhelming because we can do it for a Gaussian matrix for in a dozen of different ways. This is not a new thing, but let's try to exploit this idea for a general random matrix, let's say with Bernoulli entries. And then what we ideally would have if this small ball estimate were true, we would get that the probability that Sn of A is less than epsilon over square root of n is less or equal than C epsilon plus e to the negative Cn for all epsilon greater than 0. And if we are able to prove it for a Bernoulli random matrix, it would mean that the smallest singular value of a Bernoulli random matrix behaves like that for a Gaussian one until it breaks down, and it breaks down at the exponentially small level. And for a Bernoulli random matrix, we know that it should break down because it may have two identical rows with exponentially small probability. So this is the best we can hope for. And this is actually a theorem which holds not only for Bernoulli random matrices, but for all random matrices with IID entries and IID-centered entries with, say, variance 1. So the only thing we need to establish this theorem is this bound. And by the way, this also includes the singularity probability. If I plug in epsilon equals 0, I show that the singularity probability that a random Bernoulli, say, matrix is singular is exponentially small. But it's not only for Bernoulli, it will be true for all possible matrices. So we have to look at a very simple problem, a linear combination of IID random variables. Would it be true that this satisfies the same bound as normal? Obviously, it's not. Let's assume that the entries Aij are Bernoullis, and say the vector u has two equal coordinates, and the rest are zeros. Then, if we sum up two independent Bernoullis, the probability that this inner product is just 0 is 1/2. And so I cannot push epsilon below 1/2. This is not a big deal. This vector is sparse, and the sparse vectors are already trivial. So this problem is not serious. But yes. Yeah, yes. Thank you for the question, but this is the same thing. Let's look at this condition and write it in a clever way. Let me write the matrix A. This is A1, and then the other columns, and I call the other columns B. So B is n by n minus 1 vector. And then this condition means that B transposed U1 is 0. So the entries of B transposed are the same IID entries, and we can apply the same logic. And again, the sparse U1 would not matter. We cannot get a sparse vector in the kernel of a random matrix with any serious probability. So this vector is not a problem. But let's take the most typical vector, so to say, 1 over square root of n, 1 over square root of n, etc., 1 over square root of n. And then we have that A1 U1 is 1 over square root of n sum A1j. These are independent Bernoullis, and if n, say, is even, then to make this sum 0, I must have half of them plus 1, half of them minus 1. It's easy to figure out the probability. Is 0. This will be about 1 over square root of n. So we cannot move past 1 over square root of n, and we have to reach the exponentially small level. This vector is a serious problem. And there are others like this. There are many of those. So what is the plan if we want to prove this theorem? And may I have 3 more minutes? First of all, we already figured out that we cannot apply this logic to all vectors. So there are some exceptional vectors. So let M be a set of vectors such that our ideal small ball probability fails for some epsilon greater than e to the negative Cn. Then we have a two-step program. First, characterize we want to have some good description of this M, or at least a good description of a set which contains M. And we believe that this set is small. It's much smaller than the whole sphere. And if it is so, then the step 2 will be so that the probability that before that I conditioned on U1. Let's release this condition. And let's prove that the probability that U1 belongs to M is exponentially small. If we're able to do it, then we can continue this plus, sorry, e to the negative Cn. We can continue this calculation and say that this is less or equal than the probability that this inner product is less than epsilon, and U1 is not in M plus e to the negative Cn. But if U1 is not in M, then I know that this small probability bound holds, and we have C epsilon plus exponential Cn. We proved the optimal smallest singular value bound, and we also proved that the matrix can be singular only with exponentially small probability. We have done everything modulus this two-step program. And now let me finish today's lecture, and tomorrow we'll talk about this program and about how one can approach these characterizations. Thank you.
So are there any questions or comments? So if there are no more questions, let's thank Mark again.